Good afternoon. This is the outline for my talk. I'll first introduce the motivation for this work, which is the need for localized and controlled nanomanufacturing of nanostructures, actually. Then I'll discuss the previous work in this area. We had a previous paper with a different structure similar to the one presented today, followed by the new structure, which is called Tip Plasma Nanoprobe device, and the fabrication process, some preliminary experimental results, and summary of future work. So the motivation for this work is the basic need for localized and controlled nanomanufacturing, which is basically needed in all aspects of nanoscience. For example, if you have this capability, you could perhaps establish repairs of, like as shown in these pictures, of a mass by basically having localized the position. So you may have a very expensive mass you can repair at the nanoscale level. You could also do localized oxidation, for example, that would provide insulation between two separate nano devices. And even in the most extreme case, you could direct light nanoscale materials, in this case a silicon nanowire, on top of a substrate to position the silicon nanowire and control the size and material properties for this device. In all of these applications, you need to have the capability to deposit the material in a controlled fashion with the right orientation and the right position on the substrate. So this is specifically very important if any of these materials are going to find their way to the next generation of integrated circuits. So the approach that we have taken for accomplishing this goal is the use of basically an extended form on an AFM-tip that can do localized processing at the nanoscale. So what I describing here is so like a cartoon representation of our device. It really consists of a cantilever beam, which is attached to an AFM type of stage, and the cantilever beam has two components on it. In addition to a regular AFM-tip, it has a nozzle and it has a microchannel, and also in the nozzle you have a tip. So the idea is that we can integrate a microchannel and an electrode leading to the tip to basically generate a microplasma near the tip. So in other words, all the action is near the tip here, and then that provides an environment where you can try these various techniques for direct light, direct etching, direct deposition at a nanoscale range. Okay, so that's the concept of our device. And this slide shows some of our previous results. It was shown about a year and a half or so ago. And this shows our earlier device, and the Nanotorch device that we constructed here consists of basically a sharp tip on top of a silicon nitride beam, as you would have with an AFM tip. But then we have a series of electrodes around the tip, and we also have a microchannel. And the idea is to basically introduce the gases through the microchannel so they come out near the tip, and so you have concentration of gases at that location, and then you kind of ignite the plasma around the tip so you can have processing only at that location. There are a couple of features which are needed for this device to operate, and the first one is to have an efficient mass transfer to the microchannel itself. And the second one is to have a tip which significantly protrudes outside of the microchannel. And in earlier devices, we kind of ran into problems with both of these features, because the earlier devices had silicon tips, and the maximum height of the tip was about 6 microns, and we had to sharpen it right on top of the cantilever beam, which is made of silicon nitride. So that itself was challenging. But not only that, because the maximum tip height was 6 microns, that means the channel had to be lower than that, minus the wall thickness. So we ended up having about 1 micron channels, and basically the flow resistance through the microchannel was high. So we switched to our next design. So our next design, what we have done is we have changed most of the trouble features. We no longer are using silicon tips, but we use metallic tips, and these tips are not deposited on top of the cantilever beam, but we actually transfer. So we create a tip in one substrate, and we transfer to the substrate that has the cantilever beam. So that's completely new. If we do this type of tip, we get away from the silicon construction, and also we can make much taller tips. In fact, we use as high as 30 micron height. So that's one of the features that we have changed in the new device. And the other feature that we changed is also the type of channel. We don't use silicon nitride channels, which require silicon dioxide sacrificial layer to construct the channel. Like silicon nitride is the wall. We actually use a polymeric channel made of pyroline, which is much easier to deposit, and it's also much taller. So we have much more enhanced mass flow transfer as well as the taller tips. So that's the idea. So let me see before I go there. So generally speaking, it's difficult to construct sharp tips which are tall using microfabrication technologies. But what is not difficult to make is the inverted tip. So, and actually we happen to need an inverted tip on our substrate for making a tip. So we make inverted tips as follows. We use basically potassium hydroxide etching of 100 silicon to construct pyramidal pits. And you can adjust the depth of the pit as much as you want by basically controlling the size of your opening. And after we etch pyramidal pits onto a silicon wafer, then we passivate the surface using a thin layer of silicon dioxide. It's kind of like a spacer layer. So this is about 0.3 microns in thickness. I think it's wet. I think it's wet oxide. And after we form the silicon dioxide film, actually the other thing that the silicon dioxide film does, it kind of sharpens the tip also somewhat. And then we deposit the sacrificial layer, and for sacrificial layer we use 1 micron of spatter silicon. And you can also use polysilicon. We happen to use spatter because I believe at the time the LPCVD2 was down, so we just spattered it off on top of this. And then on top of this sacrificial layer, we put the gold, actually a layer of thin layer of chrome for addition, 50 nanometers of chrome, and 2 microns of gold. And now these 2 microns of gold, you need to at least that much thickness in order for the transfer process to work. So you need to be that thick. So the next thing that we do, we pattern the gold using lithography process, using wet etch of the gold, and we also pattern the sacrificial layer underneath, which is polysilicon. And as you can see, the polysilicon is exposed to the outside end, and everything else is coated with silicon dioxide. So that means you can release this tip by exposing to silicon difluoride. And silicon difluoride eats away the silicon and leaves the tip basically free. Now you can support the tip using cantilever beams, not shown here. We try that technique, or you can just leave it like that, and what happens as the silicon difluoride eats away the poly, the gold will fall, and you have enough addition in there. Even though you can kind of flip it, it won't fall. So it have like a good temporary addition of the tip. So this is like the construction of the tip. And then I'll show you some pictures of this kind of thing. So this shows the photographs of the tips only, actually the inverted tips, and what you get with this process. So you can see the pyramidal pit that you form with KOH. And then you can see the influence of the sacrificial layer, as well as the chrome gold deposition. So if you zoom into this surface, you can see that there's this bumpy texture out here, and the bumpy texture is really the result of our laziness, because we use spatter silicon, and if you don't have amorphous silicon, then you get these bumps. It's just the nature of the polysilicon itself. So the gold basically mirrors the bumpiness of the polysilicon. For those of you who may be wondering, you can get rid of this if you use amorphous instead. Amorphous silicon is much flatter than poly. Okay, so if you look at the bottom side of this pyramid, which is basically going to be the actual tip, it looks like this. It looks like a nice sharp pyramid, and also it's bumpiness, and again it's reflected by the sacrificial layer bumpiness. So you can see bumpiness on this side and bumpiness on that side. And if you zoom in there, you can see the nature of the tip. And my student measured the radius of these tips, and he claims it's between 10 to 20 nanometers in radius. So reasonably sharp. So after you construct the tips, then you actually have to transfer those tips to the substrate that contains a cantilever beam and all these channels. So to do that, we take a silicon wafer and we coat it with silicon nitride. I think it's lossless nitride. And then on top of that, we put another 50 nanometers of chrome, followed by 2 microns of gold. So you need at least 2 microns of gold. So you need 2 and 2. Okay. And then we come in with our aligner bonder, which is an EVG machine, and we take the other wafer that has the probe tip and just align them and press them. They are bonded by thermocompression bonding. And this is actually works very, very nicely. You can transfer the tip directly onto the substrate that we have the cantilever beam. In the next steps, we etch some openings on the nitride on the front and the back side, those are kind of access holes. And then we cover the whole thing with thick photoresist, a C9260, that's a thick layer of resist, which is about 20 microns in thickness. And the photoresist is then covered by a layer of pyroline, which is a plastic deposited from the gas phase. And we have layers anywhere between 1 micron all the way to 5 microns, or 5 or 6 microns thickness. And then we open the pyroline using oxygen plasma, leaving the structure like this. So it has some photoresist and an opening. And in the next step, we kind of process the backside of the wafer to introduce a hole that leads to the microchannel, as well as to release the cantilever beam. So it's like a standard processing of silicon nitride cantilever beams. And while we do that, we protect the entire top of the wafer using thick layer of resist. In other words, you spin more resist before you do the etching. And in the last step, you take the whole wafer assembly and you dump it into acetone, and the acetone eats away all the photoresist, and you do oxygen plasma plus cleaning, and then you are kind of like ready to release your device from the wafer. Okay, so these are photographs of some of these cantilever beams with the microchannel and the sharp metal tip near the end. And there's also a series of electrodes. There's an electrode that makes a looping here to form one of the electrodes for the microplasma. There's also a central electrode that goes right underneath the channel. Okay, and what we've shown in here is that the channel is being released basically when we rinse this in the final sacrificial etch of the resist. You can actually observe the meniscus of the water as it dries out. So it's basically you can prove that the channel is completely released, and that leads to the tip, the gold tip. And then this shows SEM pictures of how the tips looks like. This is without the microchannel, and so you can see the metal lines on top of the silicon nitride substrate, coated substrate. And the tip right there. I'll show you close-ups of the tips very soon. And then this is the same structure with the microchannel on top. And if you zoom in, you can kind of see the gold tip in there, and then the opening where the gas flow comes out and the microchannel. Actually, if you have a really good eye, you can see that this isn't quite a pyramid here, but it's kind of like it's being squeezed. And if the reason for that is that because we have actually pretty good airtight seal, is that there's actually a void here, and this, when this thing is sealed, it's sealed under under a little bit of temperature conditions. I think it's maybe like 200 degrees or something like that, a little bit higher temperature than normal. And then when you cool it down, you form a partial vacuum, so it kind of like you get this kind of collapse. If you don't make the gold thick enough, it will collapse. So it may be a good idea to have a hole in there to provide pressure relief. This is an optical photograph showing the edge of the substrate and the cantilever beam with all the electrodes and the tip right at the very top. It also shows the gas inlet coming from the back side of the wafer. So the device is kind of ready. So this is a close-up view of the exit area for the microchannel, where you can see the chrome aluminum tip, and it's much brighter in the CM that the pyroline. My student should have put a little bit of metal coating here for a better picture, but he didn't. So this is what you have. And I think I have a few more pictures of this as a closer view of the tip, gold tip. This tip is about 30 microns in height, and you can kind of see the deflection of the tip because there's some partial vacuum inside. There's a cavity with partial vacuum, but it's still good enough. It doesn't quite collapse. And this is sort of like a view from the side. Very hard for you to see, but This is a pyroline channel, and you can see the tip sticking out. So it sticks out of the hole. And I think in terms of experimental results, we have done a couple of things. These are still ongoing. The first thing that we have done is to test the suitability of these tips for performance scanning. And that's a good thing to have, because if you do any kind of localized processing, you want to kind of image the sample, see where you have etch or where you have deposit and so on. So this photograph shows an optical picture of a micromotor, and then this our device on top, which has been flipped for scanning mode, and this shows basically a capability. We can do AFM measurements with a gold tip, so you can kind of see the wires being imaged and then AFM mode. The second type of measurement that we have done, these are all very preliminary, is to determine where, which are the operation regions where we can deliver some power to the device. So we made some impedance measurements. These were done by Professor Tabib-Azar's student, and we determined that you can get maximum power transfer or minimum reflection at about 220 megahertz if you drive this thing with an AC voltage. You look at the reflection. And we have also done some, I don't know if you can see from here. Oh, I can see better on my screen. I apologize for that. We have also measured some microplasmas near the tip, but they are kind of very, very faint, and actually also you can see it at all. Can you see it here? I can see it on mine, but it looks blue here. It looks black in here. You can see. It's just maybe my angle is kind of like very large angle LCD doesn't work very well. So this is as far as we have done. We have observed the formation of microplasmas near the tip, and but this requires further study. So this is basically the summary of my work and a little bit of the future work that we plan to do. We designed, fabricated, and demonstrated Plasma Nanotorch device with a very tall tip that can be used for localized control nanofabrication. We demonstrated the releasing of a microchannel with a transfer tip on a 600 micrometer long cantilever. We have done some preliminary demonstration of localized plasma generation, but I would say that I want to say a word of caution about this, that this device has not been optimized. The geometry has been not optimized because the plasma generation on micro scale really requires further study. One of the things that can happen is that you can form plasma at the tip, or you can form plasma between your bonding wires, or between your bonding wires and the substrate. And the conditions under which you want to avoid the plasma forming in those locations and having everything on the tip, they are not quite understood. But one of the things that has influenced this kind of phenomena is the pressure. So you have to be able to pressurize it and basically play with the Paschen curve to make sure that you get the plasma at the right location. So that's something that is undergoing investigation, but we do have the capability to form the plasma location, to form the plasma at the tip if it doesn't happen anywhere else, because if you have it anywhere else, it will short out your device, it will short your tip. So in terms of the planned work, in addition to explore more of this, we want to do future integration with zinc oxide microactuators. And in addition to that, I want to acknowledge the support of the DARPA TBM program, who were kind enough to permit this work to take place under their sponsorship. And thank you very much.